for having me here. I'm quite excited. Also happy to see some familiar faces around. So yeah, today, well, some introduction. Thank you for the introduction, Virat. Yes, I am working on C4AI, on open science, open research. I've been there for a month, but this talk is about some research I did before joining the company, although it was in collaboration with some researchers from C4AI. Yeah, and the paper I'm presenting is Seeded LoRA, so collaborative fine-tuning through seed initialization of adapters. And this paper is the result of some research I did for my master thesis. But before starting the talk, I'm gonna spam you a little bit. In case you didn't know, we have C4AI research office hours. We started this week. You might know because we did spam quite a bit on the Discord server, but just in case. So feel free to join on September 25th. We will try to answer some of your questions. We will have Ahmed Ushtun from C4AI joining us. Yeah, just drop in the call and ask all the research questions you have. And that's the end of the spam. I'm not gonna talk about work stuff anymore. Back to the paper. So as I mentioned, I wrote this paper as a result of some research I did for my master thesis in the Technical University of Denmark. And I did that in collaboration with Ahmed Ushtun from C4AI, Nikki Skafte is a researcher at the Technical University of Denmark, and Tim Detmers, which was at the University of Washington and is now part of the Allen Institute. And today, oh, by the way, we are not that many, so if you have any questions during the call, just feel free to raise your hand and we can probably answer the question. If it's too complex or I'm gonna talk about that later, I will just let you know. Yeah, but today we're gonna start with some introduction. Then I will introduce Seeded LoRA, and we will finish with experiments, results, conclusions, and future work. So we're gonna start with some introduction about fine-tuning, parameter-efficient fine-tuning, LoRa, and MOEs. So just in case you've been looking at some other stuff in the last couple of years, there is this thing called large language models that are great at things like code generation or summarization or question answering. They can do many things, and they offer many possibilities. But these models might not be as good for certain tasks. So we can perform further training or fine-tuning to optimize those models for certain downstream tasks. The problem is that these models, as the name indicates, are quite large. So performing this fine-tuning is very computationally intensive. These models range from a few billion parameters to hundreds of billions of parameters. So not everybody has access to the computational infrastructure that is required to fine-tune the entire model. For that reason, there are some efficient methods for fine-tuning, we call parameter-efficient fine-tuning methods. And there are a few of these, but basically the whole idea is that they only change a small subset of the total parameters. And within these methods, low-rank adaptation, or LoRa, that was proposed by some researchers at Microsoft a few years ago, has gained a lot of popularity in the last few years. And it's mostly, and I like this method a lot, and it's popular mostly due to how effective it is and how simple it is. The intuition and idea behind LoRa is that we have a pre-trained weight, so our model, and these weights are kept frozen during the fine-tuning, and we introduce two trainable matrices, A and B, and these two matrices have a small rank, and that's the R letter we can see. So they contain way less parameters than the original model. And when I say way less, it's usually in the range of 1%, 3%, 5%, depending on the value of R that we select, and to how many layers we apply this low rank adaptation, but it's a very small percentage. So the memory requirements for fine-tuning using LoRa are way less than full fine-tuning. And as I mentioned, it is very common. It's more common than full fine-tuning. We can see here two very popular open source models, Llama 3 and Mistral 7B. And I think, yeah, we can see that in the image, we can see that fine-tunes are, for instance, for Llama 3 are like 120, but adapters are 261, like more than double. In the case of Mistral, there are more than three times more adapters than fine-tunes, which means that there are a lot of adapters already trained and available for those models. The problem is that if we want to combine adapters, it's not easy to do that. The BEF library in transformers for Hugging Face offers some options to combine adapters using different techniques. But in my experiments, the performance is not great. And there are some other techniques that allow to combine or merge fine-tune adapters, but some of those also require some additional fine-tuning. So these are two problems we wanted to solve. Also, some more background. When I was doing my research, I came across this paper from C4AI, which was a very interesting paper because they explored this idea of combining multiple LoRa adapters into one single model. And yeah, Harsha?
I'm sorry to interrupt. I just wanted to clarify. So even in standard adapters, like, and when you merge the LoRa weights, do you need to do additional fine tuning steps, or it's supposed to be somewhat lossless, right?
Yeah, so you can merge the adapters without further fine tuning, but the performance in my experiments is not great. When you merge more than 2 or 3 adapters, there is a drop in performance.
That's very cool to know. Thank you.
Yeah, at least that's my experience. If you find something different, please report that to me.
Oh, no. It just adds to my list, so it's good to know.
Yeah, but still open questions that we need to answer. But yeah, my experiments don't show great performance there. So yeah, thank you for the question. But yeah, so going back to LoRa, this paper pushing mixture of experts to the limit explored this idea of combining different adapters. So they use LoRa and IA cube, which is another BEF method. And what they do is they train the model end-to-end with different adapters, and each adapter is considered an expert, but they are trained all together. And they also include this routing layer that performs soft routing, and so basically a weighted average of these adapters. And this idea was very interesting, but it presented some limitations. As I mentioned, the adapters are trained end-to-end, and it's you don't have the option of swapping them if you want. So when I started working on this project, I had a couple goals in mind. One that I wanted to be able to merge independently fine-tuned models without additional retraining. And I also wanted to ideally get better performance than the current fine-tuning methods. So now let's talk about Seeded LoRa, now that we understand the problems. Seeded LoRa, as we can see in the image, the architecture looks very similar to what we just saw from LoRa. It's basically a set of LoRa adapters that are just put together. The difference is that we use what we call a seed expert adapter. to initialize all the fine-tuning runs. So what we do is to clarify this, we train one adapter on a subset of all the data. And then all the other experts are initialized from this adapter. And we do that to ensure that we can merge the different experts. Because, and I will explain this later, by doing this, we ensure that all the experts share the same optimization space. So what we can do now is we can fine-tune the different experts or different adapters separately, as I mentioned, using the same seed. And this can be also done in parallel. So the performance of this can be greater than training the model end-to-end altogether. And this allows us to merge all these adapters without any post-merge fine-tuning. So the main contributions of this paper and the things I find more interesting are, as I mentioned, this fact that adapters share the same optimization space. And this is thanks to, and here I have a lot of references because when I learned this, I was a bit mind blown. I couldn't believe that this was actually possible. But this is because linear mode connectivity. So when we have a neural network that is trained from a random parameter optimization, initialization, this network quickly settles into an optimization subspace. And this subspace is characterized by the principal eigenvalues of the Hessian matrix. And once this neural network has entered this subspace, the principal optimization directions remain fixed for the rest of the training. And this exhibits linear mode connectivity. So what we mean with this is that if we have two neural networks that have been initialized and they share the same optimization subspace, they can be trained on different data and they will stay in that same subspace. So this allows us to merge by just doing a simple weight average. We can do something smarter if we want, but the fact that they share this mode connectivity allows us to just do a weight average of adapters because we know they are compatible because of this fact. So this is one of the cool things we found with this project, that we can do this with LoRa adapters. The other cool thing we found, and this also kind of explains why this method works, is that our method can be seen as a sort of group convolution. There is a mathematical equivalence between our many experts and a group convolution. And this is because LoRa can also be thought or interpreted as a one-by-one convolution. So we can think of LoRa as a one-by-one convolution that first does the dimension reduction, and then another one-by-one convolution that does that recovers the dimension. So in this image, we can see how group convolutions work, and we can imagine that instead of having convolutions and groups here, each one of these is one of our adapters. So basically, the mathematical operation is equivalent. We just do a dimensional redirection here, and then we recover the dimension for the output. And to ensure this mathematical equivalence, there are a few things we need to consider. For instance, group convolutions, they aggregate through a sum. And in Seeded LoRa, we use the average. So for that, we need to make sure that the weights are initialized in such a way that they follow a standard distribution with some variance and some standard deviation. And for that, what we need is that the number of experts is equivalent to the groups. So the initialization that we need is basically a normal distribution that is centered at 0 and has this standard deviation. And for the experiments and results, and this is the interesting part. I mean, everything is interesting, but I like this part a lot. We did run a lot of evaluations. We used several data sets. So we collected a few data sets on math, code, general knowledge, linguistics, Q&A, and we train experts on each of those data sets for Seeded LoRA. We also train one LoRa adapter on all the data for comparisons, and a more LoRa model also on all the data. And all of these 3 adapters, they share a similar parameter budget. As base model, we use Llama 2 7 billion, and we ran experiments on multiple tasks. So it was a mix of language understanding, reasoning, arithmetic, mathematics, question and answering. And what we can see in these results is that for the same parameter budget, Seeded LoRa seems to perform better than LoRa and MoLoRa. And the biggest difference is in arithmetic tasks, at least in our experiments. So it seems like both LoRa and MoLoRa suffer from some sort of catastrophic forgetting, or it is, we thought a lot about what the problem could be, and it is not fully clear to us why arithmetic had these issues. So we are not sure if it's catastrophic forgetting, or we are just reaching the maximum amount of information, or because we're training end-to-end, there is a lot of different data, and yeah, it was forgetting some of it. But this behavior is not present in Seeded LoRa. And in most evaluation tasks, Seeded LoRa outperforms LoRa and MoLoRa. And when it doesn't, the difference is basically a couple of percentage points. We also look into routing issues. So we were really interested in understanding why models like MoLoRa didn't perform as well as our model that was just basically doing a simple average. And we found that routing in mixture of expert models, it's very difficult to get right. We found a few routing issues. And the 2 main routing issues that we found is that experts tend to show uniform specialization. So when you have a model like MoLoRa that is trained end-to-end, your experts are not going to be specialized on anything. And we can see that on the image in the top, that for 2 different evaluation tasks, so blue is HELA swag, red is truthful QA, the distribution of activations is basically the same. So that shows that there is no expert that got specialized on one topic and another expert in a different topic. We also experimented with top K routing to understand how that worked. And here we compare Seeded LoRa with top K routing and MoLoRa. And what we can see is that for the case of MoLoRa, there is almost a linear increase in performance the more expert you add. And what we would expect in a model that has some sort of good routing is that the first few experts, as we can see here, will contribute more because those are like specialized on something. And at some point, you reach the maximum performance, and the more experts you add, the performance will not increase, which is what happens with our model, because as I mentioned, we train experts separately on very well-defined data for different tasks. So in our work, we introduce Seeded LoRa, which allows us to perform collaborative fine-tuning. So this idea is not only that you can train different experts, but that if you are provided with this seed expert, many people can train their own adapters, and those will be compatible, and you can merge them later. We also do not require extra computation for to merge those experts. And we show that there is some theoretical foundations that link seeded LoRA with group convolutions. So this was just an interesting outcome because we can check the group convolution literature that is very established and then try to find other reasons why this works well. But there are still a lot of limitations and future work. So if this is something you're interested in, plenty of things to do. Please reach out, come to the research office hours. We can talk about that. One of the problems is that all these adapters that are already out there, they are unseeded. They haven't been trained using a seed expert. So they're basically incompatible. And that's something that you cannot change. Also, we did just a simple average. When we merge adapters, we just do a weight average. And there is a lot of limitations on that. For instance, you might want to give more weight to an expert. MergeKit is a very interesting framework, but I think that mostly works with models. I don't know if it works with adapters yet. But yeah, averaging is very limited. And you might want to give some more weight to certain experts because you know they are better. So better ways to combine experts is still needed. It's also unclear how much you can scale these type of models, like how many different experts you can add. We did experiments with up to 30 experts, and things were working fine. But how many more experts can you add? And another open question is whether there is an optimal number of experts, because maybe at some point, the more experts you add, the more noise you get in your outputs, and the more the performance decreases. So it is still an open question whether for certain tasks you want to use a different number of experts than for other tasks. And that's it. So that was fast. If you have any questions, we have plenty of time to answer all of your questions.